No, it was just trash.
Still, if you
I just don't see how you can leave. What are the reviews on? I mean, I didn't read the book, so I don't know. But, like, how could you make that like language? It's so hard to read.
It's difficult.
It's stupid. It's so long. And this is gonna come like for the whole book. In her Quizlet, she's like, I don't even know, it was about this, she's like, I wonder what this can be. Maybe he's the actual father of the baby. And this is like chapter 1. I'm like,
all right. Last night I asked you to view the video assignment for the first section of our last unit, and it's dealing with the second fundamental theorem of calculus, which can be kind of confusing, but it's actually related to some of the scenarios that we've dealt with up to this point with integrals. And there were a lot of questions which I was anticipating because it's something new, it's something different. We have variables going on that we haven't really seen before. So I just want to take a moment before we start some of the other graphical examples, kind of how this second fundamental theorem of calculus can be used. And I'm going to go back to, remember how we had a problem earlier or last week or so where we had snow on a mountain, like there was snow being added but also snow melting. Do we kind of remember that a little bit? Okay, so in general, I'm just going to say that the A of t equation is the rate at which snow is added. The L of t is the rate at which snow is lost. I'm just going to say that we're starting with 10 cubic feet of snow, which is not a lot, but it's still something. And my interval will be during the first day. Okay, so this is not in your notes. This is just an example for you to kind of see where or how this second fundamental theorem of calculus can be used. How would you want to write an equation to represent the amount of snow at any time? Okay, so we need the amount added minus the amount lost.
You also need to add the 10 because that's what you start with.
Plus the start. Okay? So can we take that English sentence and translate it into mathematical notation with the information we have at the top? How much did we start with? 10. How can we represent the amount of snow added if we have an equation that represents the rate at which it's added? Antiderivative. Okay, now what would my bounds be? If I want this to be the amount of snow at any time, 0 to k, where k represents that time, or you could use t. You could do x, right? You can do any letter you want, right, to represent that time that you're looking for. So amount we start with plus amount we add minus how can we write the amount we lost? But with L of t. Good. Okay, so I'm just going to let this be maybe the S of k equation. Okay, where k is representing the time I want to pick. So I can figure out if I plug it, if I want to figure out S of 2, that means I just have to plug in 2 here and 2 here and I'm good to go. Right? So one of the questions was that I noticed last night, why do we have 2 variables? Do you realize if I wrote down t here, and I'm kind of glad Cole used a different letter, if I were to write down t, would you guys be confused if I said S of 2? Where would you feel like plugging in the number 2? Which t's? This t? This t? This t? You see how that's confusing? Okay, so the reason that we're using a different variable is so that we can automatically tell if we wanted to plug in a value where it would go. Does that make sense?
That's why I want you to do so.
Okay, So that's one thing that I wanted to mention for last night. The other thing is, how would you want to calculate the derivative of this amount of snow? So how fast is the amount of snow changing? Can we take the derivative of this equation? What's the derivative of 10? 0. Don't even worry about it. What's going to happen if you take the derivative of an integral?
Just going to be a of t.
You would think, okay, so I understand because you didn't have a chance to watch the video assignment, but this is where the second fundamental theorem of calculus is applicable. If you want to take the derivative of an integral, you're right that you would be kind of left over with this function, but the bounds are important. So based off of last night, we would have a of k, and the derivative of k would just be 1, just like the derivative of x is 1. And we would have to subtract a of 0, but what's the derivative of 0? Just 0, okay? So whenever you're taking the derivative of an integral, you are essentially going to be left over with that original function you had, but you have to consider the bounds as well. So this is what we get by using that second fundamental theorem. We then have to subtract doing that similar derivative process here. So that would be L of k times 1 minus L of 0 times 0. I know it seems like a lot, but take a look at what it simplifies to. A of k times 1, A of k. What's going to happen over here? That goes away. Minus L of k times 1 is just L of k. What's going to happen here? 0. Okay, and haven't we seen, at least in this example from last week, that if we wanted to figure out the rate at which the amount of snow was changing, we just had to compare the individual rate equations that we started with? Okay, so this is where that concept that we used previously is coming from. We were doing the second fundamental theorem of calculus, we just didn't know it. Okay, so that's kind of an application of it. That you just didn't realize that's what was going on at the time. Okay, so we're going to take a look at this second fundamental theorem again a little bit more today, but that was just kind of an example to bring it back. The ones you did in the video assignment were algebra based, like just working with equations. We're now going to deal with some graphical examples to see how this connection can make sense. So whenever we take a look at, for instance, this function of f of x, we're letting this function be the area under g of t from -4 to 2x. Sometimes you can change the bounds. For instance, if I go back to this snow example, what do you think I would have to change if I only wanted to know the amount of snow at an even time marker? Like I only wanted to know the amount of snow after 2 hours, or after 4 hours, or after 8 hours. We would change this bound to 2k. Does that make sense? What if I wanted it after multiples of 3? Okay, it could be 3k. If I wanted intervals of odd numbers, I could do 2k minus 1. You see how you can change the bounds depending on the amount or the interval of time that you're looking for? That's probably what's happening in these cases where we have that extra piece in the bound and not just an x or a k or a t, whatever it might be. Okay, that was another question that was asked. Like why is some bound just an x and other bounds are 2x or something different? It just depends on this scenario. All right, so over here we have the graph of g. So I'm going to go ahead and write that down. Graph of g. And they're giving us this other function of f defined as the area under the g graph from -4 to 2x. So based off of this information, and if you take a quick glance at all the questions, notice how they give us the graph of g, but every question they ask us is related to f. Do you notice that? So somehow we're going to have to make a connection as to how to use this graph of g to help us figure out f information. So we're going to kind of decipher the difference. What if we want to find f of a number? What if it's f prime of a number? What if it's f double prime? We're going to see how those relate to this graph. So if I had the notation f of 0, what would you feel like doing with that number 0? If this is our equation for f. Do we have an intuition? Plug it in for what is the question? X. Okay, so notice how it's f of x, and now it's f of 0. So we're going to plug this 0 in for the x's that we have in this equation. And this is why we use a different variable, so we don't get confused. We're only going to plug in 0 up here, okay, not for these other t variables within the function. So f of 0 would be, if I plug in 0 for x up top, that would make my overall upper bound 0. So according to this equation, this value I'm looking for is the area under this G graph from -4 to 0. Do you think we can figure that out? If you were to highlight that, we want all of this area.
2 plus 5.
All right, let's do it. How'd you get it?
There's the, from -4 to -2.
Yep.
That'd be 1. Right?
From well, you have, I think it'd be 0. You have this area
Oh, well, yeah, that would cancel out. Now.
cancel out. Okay,
And
so
there's the 2 on the bottom where the rectangle is, and then the semicircle is 5.
there we go. All right, so these two areas cancel. So now we just have to figure out these two remaining pieces. So the area of a rectangle, base of 2, height is 1, and then we have to add the semicircle, not semi, quarter circle rather. So that'd be 1/4 pi, and the radius is 2. So 2 plus pi looks good. All right, so it seems like the regular f equation is just representing the area under the G graph. Let's try something similar. Okay, this time we'll plug in 2. So if I plug in 2 for x, okay, in that bound, I'm now going to need an integral from -4 to +4. So basically that's the area of my whole shape. Can we figure that out strategically? Yeah.
Well, we did half before, so just do twice the other one.
Right. Okay. So these little triangles that canceled out before are going to cancel out again on the other side, and we already know what this section was. So if we double it, because we have that symmetry, we should get this value. So if we double that, we'll get 4 plus 2 pi. Looks good. All right, so now the question becomes, what if we wanted to find the derivative of f at 1? So if this is the regular f equation, we're going to have to take the derivative of this. If you take the derivative of the left side, we can denote that as f prime. But now we have to take the derivative of the right side. And notice how the right side is an integral. So whenever you're taking the derivative of an integral, we're going to utilize that second fundamental theorem of calculus. So there's no need to work backwards because we're essentially going to be left with that beginning function that we have within the integral. We just have to be careful of the bounds that they give us. So we're going to take this upper bound of 2x and plug it into g of t. We then have to take the derivative of the upper bound, which would be 2, and we're going to multiply by that. It's kind of like the chain rule. You know how you finish by multiplying by the derivative of the inside? We're going to finish this theorem by multiplying by the derivative of the bound that we plug in. So this is what we get if we just consider the top bound. We're now going to subtract what we get, plugging in the bottom bound. So if I plug in -4, I'll have g of -4, but I need to finish by multiplying by the derivative of -4, which would just be 0. So some of you might already notice that this last piece might not even be necessary because we're going to end up taking the derivative of a number anyway. Okay, you might see that shortcut. Okay, but regardless, we now have some type of an equation to help us figure out the derivative of f. So now let's perhaps plug in that 1 that they want us to evaluate. So if I plug in 1 for x, I'm going to need g of 2 times 2. Can we figure out g of 2?
G of 2
Is 1. Okay, again, this was the graph of g. So if you're plugging in 2 into this graph, you're going to get out a point value, which in this case is 1. So 1 times 2 is going to give us a 2. All right, let's go ahead and try 4. Okay, it's something similar. This time, instead of plugging in 1, we're going to plug in -2. So here was our f prime equation. Let's plug in -2 for x. So this would be g of -4, and then we have to multiply it by 2. You can go get a drink if you need to, okay? Can we figure out g of -4? -1, all right, times 2 is going to give us -2. All right, now for our last one, notice how this is going to be a second derivative. So we're going to have to take this first derivative equation that we found. Okay, I'm just going to move that 2 on the end out front as a coefficient. But in order to figure out the second derivative, we're going to have to take the derivative of this. So let's see if we can maybe use a shortcut to help us with that. So let's see, this 2 is a coefficient. I'll go ahead and keep it. How do you want to find the derivative of g of 2x? Yeah? Chain rule, because we have an inside and an outside. So we need the derivative of the outside, which would be g prime. You're going to keep the inside of 2x, and then times the derivative of the inside, which would be 2. All right, so it seems like this would be 4g prime of 2x. So now that we have our function for the second derivative, let's go ahead and plug in 2. So I need to figure out 4 times g prime of 4. How can we use this graph of g to help us figure out this value? I heard it. Austin, you said it. We need the slope at 4. Okay, so here's our x value of 4. Here's our point. What's the slope at that point? It's an endpoint. It's negative, Austin, you're close. It's -1 before it, but what is it at that point? Undefined, right? Because it's a sharp point, we have to look out for sharp points, endpoints, and vertical slopes. Okay, this is an endpoint. So this one, we'd actually say does not exist because g of 4 is an endpoint. All right, so what we're going to be practicing with this second fundamental theorem of calculus is starting with a function that's actually defined as an integral. Okay, something that represents the area under a curve, or something that represents an antiderivative. That's what's a little bit different than any other function we've dealt with before, because it's normally represented an original function or maybe the derivative. Now we're starting with something that represents an integral. And how do we work with that kind of concept? All right, let's try another one. Given to the right is the graph of f. Okay, three line segments and a semicircle. Additionally, we have a g of x function defined as the area under this graph of f from -1 to some x value. Okay, whatever we want that to possibly be. What do you feel like doing to find g of -6? Plug in -6 where? For the x. Okay, so in our function, notice how the x represents the upper bound. All right, so we need the area under this f graph from -1 to -6. Do you notice anything kind of interesting about that integral? Yeah?
Backwards, so it's not.
We have the bounds are backwards. Okay, notice how the lower bound is actually bigger than the upper bound. So if we switch the bounds using one of our properties, we're going to have to negate it. Okay, make it negative. So -6 to -1. Okay, so whatever area value we get from this accumulation, we're just going to have to make it the opposite of what it was. All right, so to figure out the area, we'll have a triangle. So 1/2, the base is 2, height is 4. We'll then have to subtract the area of this trapezoid. So 1/2, the height is 2, and the parallel base lengths are 3 and 2. Okay, so whatever number we get from this, we're going to have to make it the opposite since we switched the bounds. So this would be 4 minus 6, which would be -2. And if we negate it, we'll get 2. Or did I switch something? This would be 5, yeah. 4 minus 5, -1. Negate it, we'll get 1. That's better. All right, let's maybe do the same thing for number 2, but this time we're going to plug in 6. So bounds -1 to 6. Now since the bounds are in order, we don't have to worry about flipping it anymore. So if we take a look, we want -1 to 6. So that looks like another trapezoid. Let's see, the height is 2, and the parallel bases are 5 and 3. Okay, that should be negative because it's underneath the x-axis. And then this quarter circle has a radius of 2. All right, so this would be -8 plus pi. Are we doing okay so far? Okay. We're going to step it up a bit. Okay, so for number 3, we're going to find the derivative of the g function. So if I take the derivative of the left-hand side, that would be g prime, and then I have to take the derivative of the right-hand side. So if you're going to take the derivative of an integral, you are going to be left with that function that you originally start with, but we have to be considerate of the bounds. So I'm going to plug in my top bound first, and I have to multiply by the derivative of the top bound, which would just be 1. Then subtract what I get when I plug in the bottom bound times the derivative of the bottom bound, which would just be 0. Okay. Again, you might notice how that's not necessary because it's just going to go away because it's being multiplied by 0. So it looks like in the end, our derivative function is just f of x. All right, so let's go ahead and plug in 6. Yes,
Wait, why does that go to f of x?
F of x times 1,
Or why is it an x instead of a t?
because I plugged in that top bound. You know how when we did the first fundamental theorem, you work backwards and you do top bound minus bottom bound?
Yeah.
That's what we're doing here, just since we don't have to work backwards anymore. So if I plug in the top bound, like instead of plugging in -6 or positive 6, I'm just plugging in a variable.
That makes sense.
You got it?
Thank you.
Okay, no problem. So if I want to evaluate this at 6, I have to plug in 6 into f. Can we use the graph to help us out with that? Two, right? If I plug in 6, I'll get out 2. All right, let's go ahead and try 4. So I have my derivative function here. If I plug in 2 for g prime, notice how that involves plugging in 2 into f. So what am I going to get? -2. Good. Something right there. All right, now this is going to bring up something interesting, because notice how before, based on the information we had, that this specifically was the graph of f, okay, the f function. Didn't we just kind of conclude here that the f function is the same as g prime? So not only is this the graph of f, but also we now know it's the graph of a derivative. And if you know a derivative graph, can't you find maxes and mins, concavity, intervals like that? So we're going to perhaps explore that a little bit more tomorrow, but at least now we're getting used to like how the second fundamental theorem works, how we can plug in values, how can we find these results. Okay, but we'll deal more with that tomorrow. All right, let's try these last ones. Find the second derivative at 2. Okay, so to find a second derivative, we know we're going to have to find another derivative after the first one. So I'm just going to reiterate, like I found before, that this was my first derivative of g. If I want to take the derivative of the left-hand side, I'm going to need an extra prime mark, and I then have to take the derivative of the right-hand side, which would be f prime. What you do to the left, you do to the right. So if I want to plug in 2 into this g prime, notice how that would involve plugging in 2 into f prime. Can we find, or can we use the graph to help us figure out f prime of 2? Why? That's good. Perfect. Does not exist because f of 2 is a sharp point. Nice. All right, let's try a different value. So if I want to plug in -4 into g double prime, that involves plugging in -4 into f prime. Can we use the graph of f to help us with that? Can we figure out the slope at -4? -2, because it says give a reason for your answer. Okay, because that's the slope of the line segment on x equals -4. That's fine. That works as a reason. Okay, it's the slope of the line around that point. Looks good. We doing okay? All right, we're going to keep trucking. Let's try another one. Different graph. We have 2 quarter circles. So we have like one little quarter circle there and a larger quarter circle there and one line segment. So this is, they tell us the graph of f. They also tell us an equation for g. So notice how g of x is this quadratic piece, but then you're adding the area under the f graph from 0 to some value, whatever that might be. All right, what do we want to do for g of 3? For what? For x. Okay, so g of 3, we're going to plug in 3 for all those x's. Okay, not t's. That's why we're using a different variable so we don't get, excuse me, so we don't get confused. All right, so 1/2, if we plug in 3 and then square it, we'll get 9. And then we're going to add the integral from 0 to 3 of the f function. All right, so 1/2 of 9, we can say 4.5. We then have to add the area from 0 to 3 of the f function. So if I shade it from 0 to 3, what's that area value? It's 0. You have the same amount above as you do below, so they're going to cancel out. Looks like our overall value would be 4.5. All right, let's try the next one. Very similar, this time g of -4. So if I plug in -4 for x, -4 squared would be 16. And I'm going to add the integral from 0 to -4 of the f function. All right, so 1/2 of 16 would be 8. What can we do for the integral piece? We got to flip the bounds, because notice how the lower bound is bigger than the upper bound. So if I flip the bounds, it's now going to change to a minus out front. So now we got to figure out the area from -4 to 0. All right, so 8 minus, and then this is going to be the area from -4 to 0. So my first little area here is a quarter circle that's negative because it's underneath the x-axis. So I'll need a -1/4 pi. My radius is 1. And then I'll add the other quarter circle, which has a radius of 3. All right, I'm running out of room, so I'm going to move up a little bit here. All right, so 8 minus, let's see, if we simplify our first quarter circle area, that'll be -1/4 pi. And then I got to add the other quarter circle area, so that would be 9/4 pi. They have a common denominator, so -1 plus 9 would be 8. 8 divided by 4 would be 2. So looks like this is just a 2 pi overall area. So my value is 8 minus 2 pi. All right, let's try the last ones, which are a little bit different. So for the bottom one, we want to find the derivative of g, and then we're going to plug in 3. So let's go ahead and take the derivative of this function they give us at the top. We're going to work through one step at a time. What's the derivative of 1/2 x squared? Just x. All right, and then I have to add the derivative of an integral. So this is where the second fundamental theorem comes into play. We're going to take the top bound and plug it into the function, so that would be f of x. We then have to multiply by the derivative of the top bound, which is 1. So if you don't even want to write it, that's okay. What's going to happen if I plug in the bottom bound? It's just going to be 0, because, I mean, if I write it out, I'll have f of 0, but then I got to multiply by the derivative of that bottom bound, and the derivative of 0 would just be 0 anyway. So that's just going to disappear after you do that second fundamental theorem. So if you notice that shortcut, that's fine. So here's my equation for the first derivative of g. Let's go ahead and plug in 3 for all the x's. So I need 3 plus f of 3. What's f of 3? -3. Good, right there. So I get 0. All right, let's go ahead and try a second derivative. So that's going to involve taking the derivative of this equation that we found in the previous example. So if I take the derivative of g prime, that'll be g double prime. And then I got to take the derivative of the right-hand side. So the derivative of x would be 1, and then I'll add the derivative of f, which would be f prime. All right, so let's plug in 2. I need 1 plus f prime of 2. Can we use the graph to help us figure out f prime of 2? Here's f of 2. Let's see, it's a line segment like Anush said earlier. Can we figure out the slope? -2. That seems about right. All right, so 1 plus -2 would be -1. How are we doing? Are we sure? Okay, are we understanding a little bit better what the second fundamental theorem tells us? It's a way for us to find a derivative of a function that's defined by an integral. Okay, much like that snow accumulation example we saw a few weeks ago. Okay, we'll do more with it tomorrow. Okay, looking at some more graphical examples, but we're heading in a good direction.